as the predictions. So, and then also at the same time call the confusion matrix again, so that it displays.
Hold on a second. The confusion matrix display does not seem to be coming automatically. I don't know why.
Okay, you
it's
can
under
just
sklearn.metrics.
Yes, it's under sklearn.metrics. So you could do this, or you could just write it. Maybe for now, since we are learning, you could write it afresh. sklearn.
I think it's not showing as part of the.
Oh, but it's working.
No. I got an error. It says cannot import confusion matrix display.
The same error I've gotten here.
Let me see, maybe if it's because of capital letters.
Oh, there's a comma there.
But I'm seeing confusion is in.
And it's a small c, but for the display, it's a capital C.
It didn't work. Not import the name confusion matrix. Confusion matrix display.
Okay, this one is a capital C.
Yeah. It's running off from your side?
Yes, running okay. But maybe just leave it for now. Just remove it and then.
Okay. Is there a way we can like import the whole library as opposed to importing the different modules one by one?
Okay, I think we can always try it.
Okay.
No, you have to specify. You have to specify the mod. Yeah, and usually sometimes it's to try make your program smaller, because if you import the whole library, then it becomes really big. So when you're not debugging, when you're compiling, it gets to be a really big program, yet it's doing a small thing. So that's what usually the aim. As just leave the other one, just import the confusion matrix alone, and then so basically this is what we'll end up with. So when you remember back from we had looked at confusion matrix and what it means. So confusion matrix, there is positive, negative. So there is the predicted values and there is the actual values. So when the machine learning program predicts a certain value to be true and it's actually true, the predicted value said it's true, and this is a true positive. And then if it's negative and you predicted it as positive, if it's positive and you predicted it as negative, then it's a false negative, and the same applies for these others. So this is what you end up with when you just do a confusion matrix, and that's what now we were checking on. So in the presentation also, we did calculation for sensitivity, specificity, accuracy, all of this. So maybe you don't necessarily have to do all these maths on your own. There is now a model that already has a function that already has all of this done for you, and that's where the classification reports come in. So classification report, you just give it the same way, and it gives you now the final score. So has everyone gotten the same? So first thing is one key one to check on, maybe before you check on all the others, is just what is your accuracy. So like this one, we've gotten 80%.
I got an error, Eric. It says prediction is not defined.
Predictions is, so check here. So for predictions, you have to make sure when you're calling your model. So first thing is, once we taught our model, or we fitted our model here, next thing you're supposed to do is create the predictions. This is what it's saying.
Okay.
Sometimes you'll see it may be written Y predict. Yeah. If you don't want to type too much, you can just call it, you can really call it anything really. So you can just call it Y predict. So I think this is what you're missing. So Y predict, or you can maintain it as we had it, or any name. So make sure you have that. It will create a matrix of supposed like what it thinks is a correct value. And you see what we are testing here is how accurately has it checked, has it predicted this. So for this time, it's given us an 80% score. Everyone okay?
Oh, just hold on.
Yes, yes, please, guys, who are quiet, I'm worried. Guys who are quiet, I'm worried, I don't know. Thumbs up if everything's okay. There is an exercise I want us to do right now. Everyone will get a different.
I got 79.
Yes, okay, that's interesting because I didn't expect different results yet. But maybe, okay, 79 is not too far off.
0.79.
Okay. So now there's something I want us to do. Everyone to just go back to this section here. So there's this section here when we were splitting the data. So add the random, you remember from this here, you can actually, from this, this was this library for train test split. So you can actually randomize the data.
Excuse me?
Randomize the data. Yes. Is this one here? Yes.
But
The audio is not very clear. Yes. Yes, Steve. Or you can post the question on the chat, please. Steve, maybe just write it on the chat. I'll be able to answer. So what I was saying is within the train test split. Okay. Okay. Maybe let me just share on this, and then as everyone tries, we'll try sort the problem, Steve. So on this function here, it has different inputs. If you don't define anything, it's going to be it takes a default value. So in all of them here, you see stratify, shuffle, all of this. There's a default value. Most of them it's none, but you can actually define. So I want us to change this so that we see if we can improve by just maybe randomizing the data. Right now, it's probably taking the first 30%. So let's see, controls the shuffling. So you can see, controls the shuffling to the data before applying the split. So so let's try just shuffle up the data and use. This should be maybe the number of loops. So just use any value there and try run everything that follows from that point. And so everyone should post what they get. So you see this has changed. Now I have a 76%. So just change the value to whatever value maybe you want, and see if you can get a better score than me. Steve, you'll share your screen, please. So let me just switch off mine. As we wait for scores from everyone. Okay. So Steve, share your screen, please.
We got 75 now.
Allow me to share. Allow me.
Yes.
Allow me to share.
Timothy, please help.
Hi, James.
Yes, Steve wants to share his screen. So, okay.
Okay.
I think, yeah, you can. He's able to share.
So, who has gotten a better score?
Mine became worse. It's 75 now.
Yeah. So, okay. Okay. Just try. Maybe the number is too big. So Steve, the error. One word missing. Why? Okay, I'm not seeing where the error is. Steve, on cell 17, the X should be capital.
Yes.
They are capital. Okay.
Yeah. Yes.
Okay.
This capital. Both of them are capital. The Y is small. The X here
Yes.
is capital.
Okay.
And I'm bringing in this.
Okay. And let me see. Extreme. Right.
Do you have curly brackets here?
No, just the normal brackets.
Like here.
It's worked okay. Steve, who's left? Yeah, so I'm waiting for everyone's results. Better results. Mercy has 78.
Can I share my screen?
Yes. Yes, please.
Sorry, not that.
Also, Steve, thumbs up if you're okay.
Are you able to see my screen?
Yes, I can.
Yes, I got 78. I used 95.
Randomization of 95.
Yeah.
Okay. Okay. Okay, that's interesting. So the next section we are going to go to is like you cannot or basically okay, that's 98. So basically there is okay, that's good, Mercy. Ernest, Harriet, Sparky, Justin, Steve,
Let's
your
share
scores.
ours.
Yes.
So we got 81.
81.
Yes.
Ah, that's interesting.
but
Mercy,
the randomization.
Yes.
The randomization we used what? I think we changed that to show 30 instead of 50. The random state.
Okay. Okay. So okay, that's interesting.
So got 81.
Anyone with a better score? Ernest? Anyone else? Better score. So I think like for the guys in banking, so you can check on there is documentation for this. So like in banking, mostly. Okay, I'm looking for the share bar. So in banking, these graphs are very important. Or also maybe not necessarily only in banking, but how we test, we'll also draw these graphs here as well. But maybe depending, you'll now use several models. Like now, I think everyone is trying, even those with maybe a less score. I think mine have tried and it's gone to 74. But like I mentioned, all of this as well are, if we go to logistic regression, if we check logistic regression, its documentation, all of these are also values you can change. You can, most of the models that work. So basically, maybe let me explain what this figure means. If this was the model being used, if you are you're in that hospital, it could be maybe a hospital. Basically, what this means is 26 people out of 100, you're going to tell them they have diabetes and they don't, and you'll get them on medication and mess up their lives. Or there is maybe within the 26 people, there are also people you're going to misdiagnose and tell them the wrong thing. So most of the time, you're trying to get your model to be as accurate as possible despite the complexity of the data. So you'll see some of the models that have been put into practice or they're actually being used in the field. They have an accuracy score of almost 98%. And 98% and 98% accuracy. It's usually like in some of the classes we've had earlier, I've shared the actual figures of misdiagnosis in the world, not in Kenya. And like for medicine, for like opticians, they have an accuracy score of like 60%. So you can imagine, like basically, I don't know if there's anyone here who wears specs, but depending on, you'll go to 5 different doctors and they'll all have different results or different prescriptions. So, and we have, I think there's an app that actually able to, I think it was being used sometime, it was being used in Kenya to check for cataracts in eyes. And it was just, you just take a picture of the eye and it had a 98% accuracy. So you can imagine comparing that with an actual doctor. So the question, like in the video I shared during the break, it's a question of, or it's more like we are now in a really big and defining stage or time, because you have machines outperforming humans. The same thing, there is a hospital in Mozambique that uses machine learning in radiography. So when pictures are taken, there's someone who normally has to interpret the X-ray. So the accuracy for humans is the same. It's really bad. Like you have someone scoring as low as even 50 or 60. So you can imagine if it's something serious and you go back to without medication. So, but with the machine learning model they have, it does 98% accuracy. So it's actually saving lives and making things way much better. So it's basically the same with this, and all these are metrics. Please make sure you just read through all these metrics: precision, recall. There is the ROC, there is the AUC that we introduced last time. All of these are very critical. So,
quick question, yes. Eric. What do what those numbers mean? The values of 1, 0, 0, 0, 0, 1, and so on. Yeah. What does that information give us? Is it helpful? And then
So-
number two,
Mhm.
now that you have this information, now that you have this model you have created, what are the
Yes.
next steps?
Okay, I'll show you the next steps. So first question, what these numbers mean. So this is a matrix. You see what we've done is we've said predict for a certain values of X tests, give us the predictions. So in real sense, what these numbers are, if you go back to this, you remember we had done the head of this. So what we really did with what those numbers are is this. They should be. So the X tests are X tests. You remember we gave certain values to X, certain columns to X. So they're all those values that were okay. So the X it's a combination of all of these columns, and there are several of them, and they're actually 30% of the whole data set that we had. So remember this data set has 768 entries. 768, so 30% of that is now the numbers we are seeing there, 101010. So based on the different values it's in. So the relationship is, and that's even why, like with logistic regression, you can use Excel to do linear regression. But when it now comes to logistic regression and the other models we're going to use, things get really complex, and even so for now it's going to be like a black box. You don't even know what's happening, how it's found the relationship. There's some articles I'm going to share on explainable AI, because now the next thing that will happen is you'll go to work and do some models and they work, and even you yourself cannot explain what's happening, but it's doing the correct thing. So there's a concept that's come up, I think, from last year called explainable AI, so that you're able to explain what your machine learning model is doing. But basically, it's found a relationship between all of these columns. There are also some columns that have more weight than others, and it's able to now give the final score. And that is now what all these numbers are. So that, and the other thing is this. So this is where we are. So we've gotten some results, and we've gotten some scores, and we are not happy. So what happens is we now go back. There's this thing called hyperparameter tuning. Hyperparameter tuning, I'll introduce that concept in the next class. There's different methods. Maybe we can just touch lightly. Okay, there are different methods we use for hyperparameter tuning. Okay, so one thing you'll see is if you change any value of all of these things, like you see there are some that are auto, there are some that are none, penalty, all of this, any of this figure will actually make the score better. So I'll actually challenge you between now and next week. Try tune all of this, not only, so I was sharing this here. So in every machine learning model has hyperparameters. These are the hyperparameters. So you can read the definition of each one of them, and it can take different values. And also at the same time, the splitting we were doing can take different values. So all of these are important. So you can imagine how complex things are now. Any comments? So there is one way of doing it. You can do literally try each one of them. So there are some, like from here, I think we had started with 100. So you can try 1 and test again, 2, test again. So I think the best score we got was 81. I've seen, there's someone, Is it an 82? So the one who got best score 81 then needs to change now something else. This one also, if you change this, you'll get a different score. And you're also trying not to overfit. So if you change this as well, if I change this, for instance, to 20%, then it's going to be different. And the scores as well, all of these aspects. So will be this what, as we learn the different machine learning models, things will change, and we have to, I think the 81% magic number was that. Let's try that. Yeah, you see now it's even getting better. So yeah, so I challenge you next week, before, we'll not use the new methods right now, but try tune this, and in the next class I'll show you a better way of doing the hyperparameter tuning. So
excuse
yes.
Kidogo.
Mm-hmm.
In practice, what I've seen happening is before you go to the prediction, you evaluate each and every parameter and find their information values, the information values and their weights of evidence. At what point?
Exactly.
At what?
Yes.
That's the next step.
So this is what you now do here, because now at least before you deploy your model, you want something that is very accurate. So you have to make sure you tune this and make sure you have the perfect ones. And even in competitions, the competitions you've seen in Kaggle, in Zindi, all these competitions, the challenge is usually in this, because everyone will get to this stage, but whoever has the smartest way of tuning this and also choosing different, there's a point we are going to combine different models, and so you have to combine different models at the same time, changing all these values. So you get a combination, it's millions of combinations of numbers that you're trying to tune, and then this section here ends up as a loop. So you're trying to loop as many times as possible and trying to get the best score possible. So that's usually the challenge, and this is even what defines now the data scientists in the field. The best one, and someone be having a better model, will make, or could easily, if it's maybe in stocks, it could or lose $1 million. Yeah, someone got 82. Yeah, so I think, and like I told you, if it's less than 90, even 95, we are not there yet. So let's try by next Saturday we have a 95 and above. Because none of this, the reality of it is you're misdiagnosing a patient, or you've lost money in a bank or something else. So yeah, or you've made a very wrong prediction and invested a lot of money in somewhere and you lose it all. So we need at least 95% confidence. Yeah. Or sometimes they say you just need to be better than the humans doing the same predictions. So yeah, like I think Elon Musk shares that a lot with the Tesla vehicles, self-driving. The error rate just needs to be better than any human being. If his machines are better than any human being, doesn't matter what any human being thinks, it's better than them. But yeah, but for now, let's aim for 95% and above. They'll introduce those concepts. There is one called grid search. There is another one called random search. There is some concepts on AutoML. So this is where things get really interesting. Any question?
What of determination of the parameters?
Which one? Which parameters?
To include or not to include?
Yes, so all of this, so just read the description. All of these descriptions, there are some that are critical, some are not. So like this one, maximum number of iterations. So you can decide to change this and do it 1,000 times and see if there's a better result. The other thing
I'm not talking of those parameters. I'm talking of the data we have. Okay, in real life scenario, what we do is after business gives you all what they think would influence the particular outcome, then you take through all those parameters through the modeling, and come up with the ones that are of value, because not all parameters that you be given that will be fitted into the model. That bit
exactly. So there's something, I think we'll see that more in the next class. So there's something called we call principal component analysis. So with principal component analysis, now there's some things that have a lot of weight, and it's like just the way you've explained, we're going to see that different columns, there are some that we can actually exclude and they will not affect the final score. So if they don't affect the final score, you could just basically exclude them. And you'll also use that as for feature engineering, and also for tuning your model. So this, like I said, this, yes.
So that is coming.
Yes, that is coming. But maybe for logistic, sometimes it's maybe not as complex. But with classification, the classification, we are going to see a lot of. There's a lot of concepts you have to consider as you're doing all of those things, and that is even maybe like when you're using Google, when you're looking for a cat, that is what will make sure you have the correct picture every time, and not you asking for one thing and getting a different thing. But it will actually help you to. I'll share, maybe let me once we're done, I'll share some code that will help you see which one is the best feature, or is the feature with the most weight. Because like you remember when we were checking on this here, depending on maybe the correlation, you might think that like for instance, which one? Maybe you'll try do the same test on the cancer. Try do the same procedure on cancer. You'll see there's a lot of relationship, like a very high correlation in some columns. Or maybe let's just look. Relation. Should be there. Correlation is usually yeah, but basically if you just check the correlation of the data, you're going to see some aspects that are very correlated, but when we do the PCA or when you do the weight checking, you realize that some columns they may be very highly correlated, but they don't have the biggest weight. And knowing that is very important, and that's where now sentiments and data are coming. You'll find someone, just because you've worked 10 years in an industry, you have a likelihood towards a certain thing. If I improve on this thing, then I get results. But it could be, you could actually be wrong, and the data actually says a different thing. And that is actually now where you find companies doing really well, because they've now moved to, instead of using people's intuition, they're now using the data to know where to actually look, and they tune things that everyone ignores, and they get better results. So so I think my exercise for you is we get this score above 95, and we do the so in the cancer data set, there is a diagnosis. So predicting, you can change, there are 2 letters here, M and B. So try you can change this to 1 and 0. 1 and 0. So yeah, try predict that and make sure you have the best score. Share your score within the week. I think whoever has the best score gets the best score as well. So yeah, I think unless there is any other question, we can stop it at that today. I hope everyone is okay. If you have a question, please don't hesitate. Question, Marcy, Justin, Moses, Steve. We are okay.
I think we'll digest that over the weekend.
Yeah, so it's I think from now on things will get really interesting and applicable at work. So try use them. There are some relationships I'm sure you've been trying to find and no one even understands what happens. But there is always, with machine learning, there is always a relationship. So yeah.
Like I had asked is once we have made the model, say for example we have made this model. So what are the next steps?
Sorry. So sorry, I didn't answer that. So what usually happens is there is something called a pico file, or basically what a pico file or what we normally do. There is a function for that that will help you to do all of that. But what we're basically doing is called serialization, or changing that from changing the model to ones and zeros that a machine can use, so that you're actually able to deploy it in an app. So in Python, there's one called pico file. So you'll create a pico file. So that pico file is now like already a model that is taught. So once it's taught, when you're using it now in an application, it's in binary form. So the application will, what will now happen, you'd now maybe have just a screen. So maybe it's a nurse in a hospital. They just take the X values. So you just tell them, measure this, put the number here, measure this, put the number here. So once they measure all of those, they put in the values, it gives them the final verdict immediately. So that pico file is now what is used in the final app, and that is what we see in most, like now on your phone. When you're talking to Siri or you're talking to Google, there's a pico file within your phone that now does all the interpretation. Some are housed within your phone, some are housed it's on a cloud. So that's how you actually now do deployment of machine learning models. And right now they're trying to get them as small as possible so that they are small enough to be within a device. So maybe I can give you some examples. Like in industry, maybe some that you could use is there's something we call vibration analysis. So how a motor is running, it usually has some vibrations, and they could be small or slowly getting bigger. So normally what we do is someone will come test, take the data somewhere, does the analysis and brings them back. But now what things are changing, and you actually have, even now in vehicles, you have a computer that has this pico file built within it. And it will listen to the vibrations and just tells you the final verdict. It tells you you have this problem, and maybe the vehicle or even the motor is still running. In industry, they are so accurate, they'll even tell you it's severe, or this is how much, this is the problem, and it will crash. It will now. I've used those, and when I was starting on them, I just told my boss, this is what will happen. We just happened to be on low season, so we could afford to do some experimenting. And several times I told the team, this is going to happen next week or 2 weeks from now. And we just decide to observe, and exactly like 2 weeks from that, the exact same thing we had predicted happens. So we've actually built confidence in the machine learning, because now it gets a bit hard to believe a machine when it just sits there and doesn't do anything. But now when you test that, you could try maybe come up with a prediction, and then if people have different opinion, you just follow it, and you several, maybe twice or thrice, you will find that it said the right thing and everyone else was wrong. So everyone else will stop maybe listening to the intuition and listen to the machine learning models. Yeah, which is usually very hard. Most of the time people don't believe the machines. So I think we are okay, unless there is any question. Timothy, you can take over. Timothy. Okay, I think maybe he's away, but anyone else with a question?
Hi, James. Sorry, I missed that.
Yeah, oh, sorry. Okay. So I think we are okay.
Yeah.
I think unless anyone has a question, we can take up those exercises given. Whoever gets the best score gets the best score as well in scoring for this class. So make sure you share your scores within the week. If you get a better score tomorrow, the one you had yesterday, it's we ignore it, we take the bigger score. Okay, that is both on the diabetes dataset and the cancer dataset. Okay, if you get 100% score, there's something wrong. So you can't get 100, you should get somewhere between 100 and 95. I'll share some articles on overfitting so you understand why 100 is not acceptable. Okay. Okay, Timothy, can take on.
That's okay, James. I have nothing from my side.
Okay. Then thank you guys. Then I think we can close the class. Okay.
Enjoy the rest of your
next week. Okay.
Okay, thank you.
Bye.
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 Bye.